Alright, so I'm going to do slide 4, the problem with the deer. You're driving down the road, down the highway, late one night, ooh, scary, at 20 meters a second when a deer steps onto the road 35 meters in front of you. Your reaction time before stepping on the brakes is 0.5 seconds, and the maximum acceleration of the car in the negative direction is 10 meters per second squared. Okay, so I'm going to draw a coordinate system. I'm going to make this way to the right positive, and I'm going to put the car at 0, and it looks like the car is moving 20 meters per second, and the deer, here's my deer. Let's see if I can draw a deer. There we go. There's some antlers. There's the deer. Oh, little tail. Haha. Okay, so, and the deer is located 35 meters. So you notice I have an initial velocity of 20 meters per second. I have a position for the deer is 35 meters. I have a reaction time. So I'm going to call that reaction time 1, change in time 1. Looks like it's 0.5 seconds. And I also have a acceleration, and this is a maximum acceleration, and that would be negative if I'm slowing down, of 10 meters per second squared. Personally, I don't like using the word deceleration. I think of my acceleration as a quantity that has direction, so it's either, in this case, it'll be either positive or negative acceleration. So here's my motion map for the car. Right? It's going at a constant speed. And now it's like slowing down after your foot actually hits the brake pedal. Should draw dots for the position of my car, right? And then over here on the left, my acceleration is 0. But then on the right, looks like I have acceleration vectors that are pointing to the left in the negative direction. So I have negative acceleration at those moments in time. Call those A. Okay? So there's my motion map. Might as well draw a stack of graphs now. Okay? And I'm going to make this simpler. I'm just going to draw a velocity and an acceleration graph. And I'm going to draw a dotted vertical line. That's supposed to be at 0.5 t seconds. Yeah, and that's 0.5. That's the moment my foot actually hits the brake pedal, because it takes me a little bit of time to react. Okay, there's my velocity, meters per second, going that way. Here's my acceleration, meters per second squared. So most of the time, just a velocity graph and acceleration graph are enough to solve the problem. And I'm going to take all my given information and just add it to my graphs after I graph the shapes of my graphs. My velocity graph should look like this, because constant velocity until my foot hits the brake. And then this is the slowing down period, right? And my acceleration is 0, again, until my foot hits the brake. And then I have a negative acceleration, okay? And let's see here. Let me erase this a little bit. Oh, not erase all that. What was that? There. Okay, now I can fix it. So my acceleration, I'm going to stop it right there. Okay? And it looks like my acceleration, assuming I utilize my maximum acceleration, and I have a good braking technique, say it's negative 10 meters per second squared. I'm slowing down 10 meters per second slower each second, right? And, well, let's see what I can figure out. I think right away, oh yeah, I also have this number here. There we go. And I can find this area right off the bat. That's going to be 20 times 1/2, which is 10. the units will be meters. So that's my displacement before my foot actually hits the brakes, right? And I don't yet know what moment in time this is, right? But I do know that, I know this area here is my change in velocity, right? And it looks like my change in velocity while I'm slowing down should be a negative 20 meters per second. And I'm going to call this amount of time t, okay? I'm just going to call that t. So my change in velocity has to equal my acceleration, which is negative 10 meters per second squared, times t. So if I solve that, I get t equals 2 seconds. So that tells me that my final time when I stop should be 2.5 seconds. That means this is 2.5 seconds, right? And that'll allow me to find my displacement while I'm slowing down, right? So my displacement when I'm slowing down, since that's a triangle, is going to be 1/2 20 meters per second. That's the height of that triangular shape. Times 2 seconds. That's the time by which I'm slowing down, right? Okay, my seconds cancel. I'm left with meters. So that's 10 times 2, which is 20 meters, right? So if I add these two displacements, my total displacement should be 10 meters plus 20 meters, right? Which gives me 30 meter displacement. And that means that I am still 5 meters away from the deer. Okay? And I'm pretty sure that's what the question was asking. How much distance is between me and the deer when I stop? Well, if I utilize 10 meters per second squared worth of acceleration, I should still have 5 meters left when I'm stopped. Okay? So maybe my car is like right there, and I haven't hit the deer yet. I hope that helps, and that's my version of how to solve number 4. Okay? Have a good day. Thanks for watching.